Hello friends, last time we discussed about practice examples related to particulate matter control devices. So, today we will discuss upon several examples which are related to gaseous emission control devices. So, basically we will include the mechanism which governs the control devices or on the mechanism on which it is based, those devices like adsorption, absorption, oxidation or condensation. These are basic physico-chemical principles on which gaseous emissions are controlled. Okay. So, those devices are based on these particular principles. So, we will look into one by one, and before that I would like to highlight some data which can be used here, because we have taken several examples from FPS system. So, basically if you want to convert them into this SI units, international systems units or metric system, then these are the basic conversion factors which can be readily used. Well, so for example, we go for a dry cleaning process exhaust, means exhaust emissions are there and that air stream is having like standard cubic feet per minute exhaust emission of 15,000 SCFM, that is standard cubic feet per minute air stream exhaust, okay, and that contains around 680 ppm this carbon tetrachloride CCl4, okay, carbon tetrachloride. So, we need to determine the saturation capacity of the activated carbon which will be used in this adsorption system. So, these adsorption isotherms for carbon tetrachloride on activated carbon which we use. So, we have to determine what is the saturation capacity, and we have to assume that the temperature and pressure of exhaust stream are approximately around 140 degree Fahrenheit and 14.7 this PSI, that is the pounds per square inch, okay, in absolute terms. So, these are the values which are given. So, basically you can see the given values are of the exhaust system, exhaust stream system. Flow rate is around 15,000 SCFM, that is standard cubic feet per minute. Volume of the carbon tetrachloride is 680 ppm, temperature and pressure is given. So, we need to convert first of all the mole fraction, that is because 680 ppm is given. So, basically you can call it 0.00068 fraction. In fraction volume it is in percentage or in ppm we have to convert. So, in percentage volume 680 ppm will be known as 0.0068, okay. So, this is the fraction basically. Then we can see this partial pressure. So, partial pressure we convert this 14.7 pounds per square inch which can be multiplied by this fraction, that is 0.0068. So, we get this partial pressure of CCl4, that is the carbon tetrachloride, and that is around 0.010 pounds per square inch in absolute terms. Okay, then we have this plot which can give us the value of percentage, this capacity weight in percentage per 1000 pound of the carbon. Okay, so, we go for this value which we have determined 0.01. So, 0.01 we go for 140 degree Fahrenheit, this particular plot, and go on the left side, and we get this value is around 40%, and that is per 1000 pound of the carbon. So, basically we can say that 40 gram of the vapor per 100 gram of the carbon is the saturation value, you can say. Up to that only it will be removed. The next example is related to dry cleaning process, the same example basically which we have seen. So, here values are same, 15,000 SCFM, that is standard cubic feet per minute of the stream flow, and 680 ppm of carbon tetrachloride is there. We need to estimate the required amount of carbon which will adsorb in 4/4 cycle, okay, and this exhaust stream is again operating with the same temperature and pressure. Here we have to note that the saturation capacity of the activated carbon is 30% by weight, this is given, okay. Then molecular weight of CCl4 is 154 this pound mole, you can say, like gram mole we represent in SI system or metric system. Similarly, this is pound mole. Then we need to use working capacity of 25% of the saturation capacity. So, we need to use these values to estimate the total requirement of the carbon which will absorb this total carbon tetrachloride, right. So, again those are the values which are given. Fraction 680 ppm we can represent into 0.0068, then temperature is given, pressure is given. Okay. Now, we need to calculate flow rate of the this carbon tetrachloride. So, flow rate means you have to multiply this flow this SCFM into the fraction which we have done 10.2 SCFM of the CCl4, that is the standard cubic feet per minute. Now, we can convert it into this like pound mole per hour. So, what we need to do? We need to multiply this value of 10.2 SCFM with this pound mole. In how much cubic feet pound mole is related. So, here value is given. To convert SCF, that is the cubic feet, okay, to pound mole, we have to use this particular factor basically, because this cubic feet is per pound mole it is used, right. So, we have to multiply that and then we can convert minute into hour. So, ultimately we can say that this is the pound mole of the carbon tetrachloride per hour, okay, in this particular flow rate. So, for a 4 cycle, 4 hour cycle, okay, 4 hour cycle, basically you need to multiply this value with 4 hour, because that was the per hour value. So, 4 hour means 980 pound mole of carbon tetrachloride will be adsorbed or removed. Now, what we need to see? The saturation conditions. The activated carbon which is using this particular mechanism and removing around 30 pounds of the vapor for every 100 pounds of the activated carbon, that is the 30%, right. So, with that value you can use these 30 and 100 value and convert this 980 pound mole into total pound mole activated carbon. This was the value of carbon tetrachloride. So, for removing that particular value we need this much of amount of the activated carbon, right. So, given the working cycle of 25% of the saturation capacity, only 25% it is working. So, you divide by 0.25, then we will get total amount of the activated carbon, we divide by 0.25. So, we get this much amount of the this carbon per hour 4 hour cycle of the adsorber basically. Next, we have to see this regenerative carbon bed system which has 3 beds in parallel basically, and it is removing the gas flow rate of this 9000 SCFM, temperature is given, gas pressure is given in terms of water column. Now, please always pay attention to the units. It is very important when we are calculating something, then we have to give proper attention to the units. If we do not use proper units, then calculations will be erroneous and our design of the instrument will be totally wrong, and we will not achieve those objectives or goals we want to achieve for removal of the air pollutants. So, barometric pressure is around 30.3 inch of the mercury. So, what is the minimum cross sectional area of the each bed if the gas velocity must be maintained below 100 feet per minute. So, those values are given and we have to estimate this minimum cross sectional area. So, again first of all put all the values which are given in the problem statement. So, the given gas characteristics are flow rate is this much, then temperature is given, gas pressure is given in terms of water column, barometric pressure 30.3 inch mercury, gas velocity is also given. Okay. Now, we estimate this absolute static pressure, okay, SP absolute. So, you can convert this 4 inch of this water column plus 30.3 inch of the mercury, you convert into water column again, 29.92 of the mercury, 407 inch of the water column. So, we get the value of 416 inch of the water column. Gas flow rate 9000 SCFM given, temperature is given. So, you can convert and you get this value of ACFM, that is actual cubic feet per minute, and that is the value of 9340 of the actual cubic feet per minute. This is the value. Okay. Now, this value basically velocity, how to represent velocity? Flow rate divided by the area, and area we need to calculate basically. So, velocity is given 100 feet per minute, this is given basically. Gas flow rate you have just calculated 9340 SCFM. So, put these values and area is the unknown. So, we take take area here, 100 here, and ultimately we get this value 93.4 square foot. So, this is the minimum cross sectional area of the each bed which will be required to adsorb that amount of particular gaseous pollutant. Next is related to absorption. So, we need to compute the minimum liquid flow rate of pure water required to remove 90% of the sulfur dioxide from a gas stream of 85 cubic meter per minute or 3000 ACFM in FVS unit containing 3% of the SO2 by volume, that is gallon per minute, and the temperature is given 293 degree Kelvin, okay, and pressure is given 101.3 kilopascal. Henry's law coefficient or constant is given as 43. So, we need to use these values. These are the flow chart, and you can use those values. It will give easy visualization. So, the given values, flow rate is given, SO2 concentration by volume is given. Okay, now in gas phase, 0.03, 3% is 0.03 fraction, basically 90% of SO2 is to be removed, right, remember it, okay, and 10%. So, basically remaining SO2 concentration 10% in the inlet, 0.003 is the fraction, okay. These values we have to use, and 43 value where it is coming from, you can see 43 is the constant value, Henry's coefficient you have to use. So, you can use those values and get these minimum liquid gas to ratio Y1 minus Y2 equals this moles water and per gram moles of the air. So, these equations are used, very simple relationships which you can put those values and get the value of around 38.7 gram mole water per gram mole of the air basically. Then given the flow rate, how much, 85 cubic meter per minute. So, at 0 degree Celsius this 101.3 kilopascal pressure is given. So, there are these kind of cubic meter per gram mole, those ideal gas values, right. Then at 20 degree Celsius you can convert those values, that is 0.024 cubic meter per gram mole. Now, we have to use this again relationship. So, 38.7 we just calculated, 85 cubic meter per minute, that is 3540 gram mole per air per minute, that value is there. So, we multiply both and we get this value into gram mole water per minute, that is this 137,000 gram mole water per minute, okay. So, then you can convert it into cubic meter per minute by this particular relationship. So, that way you can, this is the value basically we wanted to calculate, minimum liquid flow rate. So, this much is the minimum liquid flow rate which is needed to achieve that particular targeted value. Next is related to calculation of amount of calcium hydroxide or lime which is needed to neutralize the HCl absorbed from a gas stream having 50 ppm HCl and a flow rate of 10,000 SCFM standard cubic feet per minute, okay. Assume this HCl removal efficiency as 98%. So, these are the given values. You can use this particular equation which 2 HCl plus CaOH hydroxide, calcium hydroxide plus 2 Ca plus 2 Cl minus and plus 2 H2O. So, basically you can see 1 mole of lime or calcium hydroxide is removing 2 moles of HCl. So, that we need to remember, right. So, the HCl concentration 50 ppm, that is 50 into 10 to the power minus 6, okay. This pound mole of the HCl, flow rate is given, 98% is the removal efficiency. So, use these values and multiply and you get values of the HCl in terms of mole, this pound mole of the HCl per minute. So, these values can be put in this particular very simple arithmetic and relationships are there. Then you get this value of just got 0.00123 pound mole of the HCl per minute. So, they are the same value. Now, how much calcium hydroxide is required? So, we know basically this pound mole per minute, you can convert it into the pound, this 74 this value particular calcium hydroxide, and you got this 0.0455 pound per minute, that is the 2.73 pound per hour, because you can multiply it by the 60. Hence, the amount of calcium hydroxide lime needed to neutralize the HCl absorbed as 2.73 pound per hour, okay. This is the molecular weight in terms of this. Now, next example is related to thermal oxidizer. So, we have seen adsorption and absorption related mechanism or devices we need to design based on those principles. Now, oxidation process is there. So, a thermal oxidizer is there which controls emissions from a paint baking oven, okay, and the cylindrical unit is there which has a diameter of 5 feet, or you can say radius is 2.5 feet and a length is 12 feet. So, we need to remember when we calculate the volume of this particular cylinder, with all combustion air supplied by an auxiliary source, and the exhaust from the oven is 8000 SCFM, standard cubic feet per minute, and the oxidizer uses 300 SCFM of natural gas and operates at a temperature of 1400 degree Fahrenheit. What is the residence time in the combustion chamber to remove that particular pollutant? Okay. Assume the fuel is 100% methane and that the burner is being operated at 125% of the stoichiometric requirement. So, those values we will be using in this particular problem. So, we have this combustion reaction methane, it oxidized by oxygen and converted into CO2 and 2H2O, okay, this water. So, stoichiometric oxygen requirement is 2 moles of oxygen for each mole of the methane, we have to remember that. Okay. You use this particular values which are given 300 SCFM and this 385.4 cubic feet per pound mole is used for conversion into SCF, that we have earlier also used. So, convert that into pound mole of the methane per minute, okay, these values, and because we know 2 moles of the oxygen required. So, twice of this particular pound mole of the methane will be required as oxygen, and you can convert that value into this pound mole of the oxygen per minute, because this value is to be used as per CH4 and those molecules. Next is the total oxygen requirement, okay, because 125% is the stoichiometric requirement. It does not go like purely 100%, you need more. So, 1.25 times of the stoichiometric requirements, you multiply by 1.25 you get this value 1.95 pound mole of the oxygen per minute. Now, how much nitrogen will be there in the air? You know the relationship, around 21 percent of the oxygen and 79% of the nitrogen is there. So, you use this particular relationship and you get how much nitrogen, this is 7.37 pound mole of the nitrogen per minute will be there. Next is like this flue gas flow rate. So, flue gas flow rate is basically the exhaust gas which is heated plus product of the combustion plus nitrogen and excess of the oxygen which we have calculated. So, exhaust gas is given 8000 SCFM, products of the combustion are CO2 plus H2O after this oxidation. So, CO2 you can calculate by this particular relationship, the relationship H2O. So, the total of the CO2 and H2O is around 2.34, around 1.56 plus that 0.77 or 0.78 you can say. So, 2.37 pound mole per minute of the total exhaust is there of the CO2 and water vapor you can say. So, 2.34 you can convert into this SCFM again by multiplying this particular factor. So, 902 SCFM is the value. Now, next is the oxygen consumed, how much oxygen is consumed as per stoichiometric requirement, we have calculated already around 1.56, you can see here 1.56, okay. Then amount of the oxygen remaining, so total minus consumed, so 1.95 minus 1.56, so around 0.39 is excess you can say. Nitrogen excess, total N2 plus O2 remaining, so total is around 7.76. So, 7.76 will be the axis that can be converted by multiplying by 385.4 SCF that factor. So, SCFM that is 2990 standard cubic feet per minute. So, the total flue gas flow rate is the 8000 which is given plus 902 which we have calculated just now here, and then this excess one 2990. So, total is 11900 SCFM. Now, step 5 is conversion of the flue gas flow rate to the actual conditions, ACFM, actual conditions. So, this 11,9,000 SCFM you can convert into ACFM. So, you can have these temperature values. So, you can convert into like 41,900 ACFM. Now, next is calculation of the volume of the combustion chamber. So, we remember the radius 2.5 feet was the diameter. So, 2.5 feet is the radius. So, 2.5 square pi r square is the area and into length. Okay. So, this is the volume, length is 12 feet, it is given. So, 235.5 cubic feet is the volume of that chamber. Okay. So, the residence time very easy now, you know the chamber volume, you know the volumetric flow rate. So, divide the this volume of the chamber by volumetric flow rate, you will get the residence time. So, this value is divided by this flow rate, that is the actual one, and you get around 0.00562 minute. Okay. You can convert it into milliseconds, so around 337 millisecond, very quickly you know this process happens. So, that is very efficient, you can say. So, 337 milliseconds is the residential time in that particular combustion chamber, and you get the results. Next is like now condensation. So, we have seen adsorption, absorption and oxidation. Now, the process is condensation. So, in condensation, what is the maximum toluene removal efficiency? This is one problem possible in a refrigeration type condenser operating at 100° Fahrenheit if the inlet concentration is around 10,000 ppm. Okay, and the given outlet partial pressure at the this temperature 100 Fahrenheit is how much? 0.015 millimeter of mercury. Okay, you know the conversion of those systems. So, need not to worry, you can use those. So, inlet concentration is 10,000 ppm. Okay, given the outlet pressure at 100° Fahrenheit is given this much. Now, assuming the outlet gas stream is in equilibrium with the toluene condensate. So, the outlet partial pressure determines the outlet concentration, and the conversion of outlet concentration to ppm can be done easily. So, the outlet concentration by this you can convert this 10 to the power 6 ppm, and these you have values, you can convert that is around 19.7 ppm. Now, removal efficiency in minus out, inlet outlet divided by in and multiplied by 100, right. So, 10,000 is inlet, outlet how much? This we have calculated 19.7 divided by 10,000 and multiplied by 100. So, around 99.8% is the removal efficiency, wonderful efficiency basically. Next is determination of the following for a condensing system to remove VOCs, volatile organic compounds, from an air emission stream. So, we need to determine the partial pressure of the HAP, that is hazardous air pollutants, okay, in the condenser effluent. Assuming the pressure in the condenser is constant and at atmospheric, okay, level. Determine the condensation temperature, okay, from the given plot. So, plot is given, these are the values, okay, maximum flow rate is given, temperature is given, what is the hazardous air pollutant which we are dealing with, it is also given, this is styrene. Then this concentration is also given 13,000 ppmb by volume corresponding to saturation conditions. Moisture content is negligible, we can just neglect it. Pressure is given 760 mm, okay, removal efficiency is 90%. So, we have those values basically. So, partial pressure you can calculate easily and you get this value around 13,000 ppmb already given, right. So, use those values and calculate partial pressure around 1 mm of the mercury. So, that would be the partial pressure, and using that particular partial pressure you can get the value of the temperature. So, that is basically from this graph, and it is around 20° Fahrenheit, because 0.00208 is this is logarithmic graph. So, basic value is 20° Fahrenheit. Next is determination of different design parameters like the moles of the HAP in the inlet emission stream, then moles of the HAP in the outlet emission stream, HAP outlet, this is emission stream, moles of the HAP condensed, okay, and in heat of the vaporization, HAP is hazardous air pollutants, heat of the vaporization. The this enthalpy change associated with the condensed HAP, okay, that is also be determined. Then enthalpy change associated with the non condensable vapors, that is air, okay, that we have to calculate. Then condenser heat load, that is the H load we need to calculate, and the values which are given are these one. This flow rate is there, temperature is there, name of the hazardous air pollutant is also given, all these values are given as the earlier one. So, this given data is there, then simple relationships again you can just calculate those values, multiply with those, keep in mind the proper units. So, these values are given, okay, you just multiply by the respective coefficients and the conversion factors and you get the values. Okay. Similarly, like here you got this value, and similarly this moles of the HAP in outlet you can calculate. So, all those simple calculations are there. So, I can just quickly go, and then heat of the vaporization is there, this can be taken from the chemical engineer's handbook, because these design parameters are there which will be used for designing of the instrument. So, as an engineer you have to be very much convergent of these design parameters. You got this value from this chemical engineer's handbook. Okay. Then enthalpy you can calculate with these relationships which are simple calculations, okay, plus minus addition subtraction those. Similarly, the enthalpy change associated with the non condensable vapors also can be calculated in the similar fashion, and the condenser heat load again same those emission factors and those values are there, and heat and this energy per minute of the values are there. So, you can multiply and add those values and you can get the total value. Similarly, in the this example next example is to determine those parameters like logarithmic mean temperature difference, condenser heat exchanger surface area, then coolant flow rate, refrigeration capacity, then quantity of the recovered product we need to go for recovery. So, these are the given values and we have to use and determine these coefficient. So, again use these given values and convert them into the desired parameters, and you can calculate whatever like condenser heat exchanger you can calculate by these kind of simple empirical equations, right. Coolant flow rate also you can calculate by this particular relationship, ultimately 14,700 pound per hour of the coolant calculation is there. Refrigeration capacity, okay, so this much value we know because this H load is there. So, that you can use, and this capacity divided by 12,000 and this 20 tons is the estimated value. Then quantify of recovered product, so you can use other those values and ultimately you can get this 373 pound per hour. Okay. So, in conclusion basically we can say that all these principles which we have seen like adsorption, absorption or oxidation and condensation, these simple principles are there, and of thermodynamic kind of relationships are there which we have to use, and we need to calculate whatever desired parameters are there, so that our instruments can be designed properly and they can function on the desired efficiency. Like in the given examples we can see that the adsorption of the saturation capacity of the activated carbon was around 40% by weight. Removal efficiency of the gaseous pollutant in the absorption we could see around 98% it was there. Residence time was very less, 338 kind of milliseconds, which is very less. So, it can show that it is very efficient mechanism, and the condensation removal efficiency greater than around 99.8% could be achieved. So, these are the examples, practice examples. When you go at leisure properly in a focused manner, you read the statement, problem statement very calmly, and then go step by step, so that you can calculate those parameters, and that way you will be like a design engineer for designing the equipments or processes or mechanism which are required to remove the gaseous air pollutants. So, this is all for today, and these are the references wherefrom we have taken these practice examples for you. So, I advise you please practice these examples whenever you get time. So, you will learn and you will appreciate how these design parameters are really helpful for removal of gaseous air pollutants. So, thank you for your kind attention. This is all for today. See you in the next lecture. Thanks.